This is the introduction to exercise 6.3 on... Let's try that again. This is the introduction to exercise 6.3 on global maximum and minimum. We start off with our do now question here with a identifying function families question. We have a curve with the equation of y equals to x cubed plus ax squared plus bx plus c passing through the point 0, 5 and having a stationary point at 2, 7. Find the values of a, b, and c. The easiest one for me to identify, of course, is the c, because it says that when x equals to 0, y equals to 5. So if I'm going to write that in proper form, it's 5 equals to 0 plus 0 plus 0 plus c. Therefore, c equals to 5. Great, we can leave that there. Well, I know the new equation is now going to be y equals to x cubed plus ax squared plus bx plus 5. And the next bit of information I'm going to use is the 2, 7. There is a point at 2, 7. Therefore, when x equals to 2, y equals to 7. So I'm going to have 2 cubed plus a 2 squared. I'm going to write a times 2 squared. Plus 2b plus 5, which should give us 7 equals to 8 plus 4a plus 2b plus 5, which simplifying that down, I get 12 plus 4a plus b equals to 0. Is that a bit hard to see up the back? No? Okay. Any questions so far? No? Okay, well, let's read this properly. So it says 7. I'm going to have 7 equals to 13 plus 4a plus 2b. Yeah? When I transpose that, move the 13 across, shouldn't that give me negative 6 equals to 4a plus 2b? Don't blindly listen to me, please. Just tell me when I'm wrong, yeah? All right, let's keep going. So we've got that function. The other thing I'm going to do is it says there's a stationary point at 2, 7. So I need my second equation from the second bit of information. Therefore, I'm going to go ahead and find my derivative, which in this case, I'm going to write dy dx equals 3x squared plus 2ax plus b. Of course, when let that equal to 0, so I'm going to let dy dx equal that, which equal to 0. I should end up with a value of 2, right? So as in x should equal to 2. When x equals to 2, the stationary point is at 2, 7. Therefore, dy dx equals to 0. So I'm going to put in 3, 2 squared plus 2 times a times 2 plus b equals to 0. That's 8 plus 4a. Not 8, sorry. 12 plus 4a plus b equals to 0. Any questions? From there, it's just a simultaneous equation situation. I'm going to rearrange, let's say I'm going to rearrange this one to get 4a equals to negative b minus 12. Reason I'm just sticking with 4a is because that's an easy substitution into the other equation. So substituting that back over here, I get negative 6, and I'm replacing 4a with negative b minus 12. So negative 6 equals to negative b minus 12 plus 2b. Add 12 on both sides, gives me 6 equals to b. Done? Why not? Thank you very much. We need to find a as well, and preferably you need to say a, b, and c equals to etc. So to find b, I'm going to substitute that back into one of the equations. I'm going to put that back into here, right? And that gives me 4a equals to negative 6 minus 12, which simplifies into, apologies for the lack of space, a equals to negative 9 over 2. So now I'm going to write therefore. It's not pretentious to write therefore, by the way. A equals to negative 9 over 2, b equals to, what does that say, 6, and c equals to 5. Any questions? Okay. Sweet, let's move on. So for this exercise, we're focusing on the idea of global maximum minimum. Another name is absolute maximum and absolute minimum. Doesn't matter which one you use as long as you can recognize that they mean the same thing. So stationary points can be a local maximum or local minimum. We talked about that in the previous one, but we also said that they're not necessarily the absolute / global maximum or minimum. The actual maximum and minimum might actually be dependent on the endpoints, or it might even be dependent on the fact that it goes towards infinity. So let's see what that looks like. In this question, it says find the absolute maximum and minimum value of function f given by the rule. Now for me, of course, I'm identifying the fact that it has a set domain. It's a restricted domain. And it says it goes towards all real values. It's not telling you that the range is all real values. It's saying that the range is not restricted in what will be what you're working with, right? So specifically, you've got a domain, you need to find that range, okay? Because it says find the absolute maximum, absolute minimum. So first thing I'm going to do is substitute -2 into our function. So if I get f of -2, that gives me, and I'm going to skip a couple of steps, it gives me 4 plus 4 plus 2, so plus 2 plus 2, there we go, which is 8. So I know that -2, 8 is a coordinate. I'm going to substitute my other end of my restriction, so f of 4, which gives us 16 minus 4 plus 2, which gives us 12. 14. Maths is hard. So the coordinate ends up being 4, 14. They're not necessarily my maximum minimum. I'm just saying that those points exist, and those are the end points on my graph. The really important factor is to now identify what does the graph look like. Luckily for us, this is a very nice, easy parabola. X squared minus x plus 2, of course, it's a positive parabola. It's a happy parabola. It's going to be a smiley face, right? It's going to have a minimum. It's going to have it's not going to have a maximum unless it's defined by a restricted domain. Let's find our x-intercepts, right? X-intercepts, that's x squared minus x plus 2 equals to 0. Let y equal to 0, right? Cross method doesn't really work here. I'm just going to complete the square, and I get x minus half squared minus a quarter plus 2 equals 0. I'm not going to bother continuing this process because I don't know why. True. You know what? I didn't even think about that. You're right, but I'm not going to bother trying to find the x-intercepts. There's a reason for that. You know, I'll just keep working through this so I can show you what I mean. X minus a half squared, that becomes 7 over 4. So plus 7 over 4 equals 0. Where's the turning point? It's half 7 over 4, right? It's a positive parabola. If the turning point is going to be above the x-axis, there is no x-axis intercept. And if you keep going, you'd end up with a square root of -7 over 4, which means there's no solutions anyway. So we're good. The turning point is at that, so I'm going to go ahead and very roughly sketch that here. It doesn't need to be perfect, just roughly is fine. I'm going to say that's about, let's say there, that's a half and 7 over 4. I draw my graph again very roughly. I'm not going to do this because there is a restricted domain. Specifically, my restriction goes towards 4, 14, and the other one goes towards -2, 8. So it looks something like this. My absolute maximum is therefore at 14. And my absolute minimum is going to be 7 over 4. Note how even though the turning point is a minimum, or in this case the turning point is the minimum, great, but it's not necessarily always going to be the case. Especially if you have cubic. If your cubic looks like this and you're restricted like this, I'd say that this point is significantly lower than this point. So have a graph, find the key features, and then once you've done that, identify which one is indeed your maximum, your minimum, etc. Questions? Let's look at a word problem before I let you go. So, example 19. A farmer has sufficient fencing to make a regular pen of perimeter 200 meters. What dimensions will give an enclosure of maximum area? The first thing I'm going to do is set my domain, right? So I know, just generally speaking, let's call that x and that y. If the perimeter is 200, what is the restricted domain of my x and y values? what can x or x and or y be? Anything above 0, so I'm going to say from 0. Now, there is a debated argument within the maths assessment in saying, can x technically be 0? My argument is no. If you lose one side, it's no longer a two-dimensional shape. So, anything above 0, is there a maximum? 200, exactly right. Remember that we have enough for 200. Now, a lot of you might instinctively think, well, it's x and y, so therefore shouldn't it be 100? Not necessarily. Okay, because remember, y can be less than 100. Alright, so what dimensions were given enclosure of maximum area? First thing is we're given a perimeter formula. Let's find the perimeter. I know that 2x plus 2y will equal to 200. Because it's maximum, right? I'm going to say I'm going to use all of the perimeter. Of course, rearranging that, I get x, let's just divide by 2 first. X plus y equals to 100. X equals to 100 minus y. Okay. Now, of course, I've got my area formula, which I know is xy. I'm going to write area equals to xy, which equals to, I'm going to replace my x value, so 100 minus y, multiplied by y, which gives me an answer of 100y minus y squared. I'm trying to find, that's my function now. I'm going to define it. Let's say, and I'm running out of space, apologies. Let's a of y equal to 100y, sorry, minus y squared. Which means that if I find dA dy, and it looks weird, but it's the derivative of the function a in terms of y, that becomes 100 minus 2y. I'm going to go ahead and find my turning points, right? I mean, it's a negative y squared. It's going to be a sad face parabola, which most area, volume, etc. formulas will be, by the way. And then I'm going to just identify that because it's a parabola. It's very clear parabola. The turning point is going to be a maximum. I don't have to worry about absolute versus a local maximum. So I get let dA dy equals 0. I get 100 minus 2y equals to 0, or y equals to 50. And you probably could have figured this out without all this calculation, that the largest area is when all the sides are the same anyway, it's a square. But that's the mathematical proof. You would then write x equals to 50, y equals to 50. Again, do note, in this case, I can just look at the function and know, because it's a parabola, it's going to have the turning point as the maximum, both absolute and local. Again, that would not always be the case. Any questions?